Imagine traveling through time, not just back a few years or even a few centuries. Imagine a journey that takes you all the way back to the very beginning, to the birth of everything we know, the birth of space, the birth of time itself. We are about to embark on that journey. It is the greatest story ever told, because it is the story of everything. It is our story. We will start when the entire universe was smaller than a single atom and hotter than anything we can imagine. Our grand tour will take us through 13.8 billion years of cosmic history. This is a number so vast it's hard for our minds to grasp. So let's compress it. Let's imagine the entire history of the universe as a single calendar year. In this cosmic calendar, the Big Bang happens in the first second of January 1st. Every month, every day, every hour that passes represents millions and millions of years of real time. We are, in the most literal sense, stardust. We are the universe made conscious, so get ready, and it starts now, with a single explosive moment that changed everything forever. Let's go back, all the way back, before the Earth, before the Sun, before any stars or galaxies. We journey back to a time before time itself, as we know it, existed. We arrive at a moment 13.8 billion years ago. The entire universe, everything you've ever known or will know, was compressed into a point of unimaginable density and heat. A point smaller than a grain of sand, smaller than an atom. There was no space, there was no time. There was only this single, fiercely hot, infinitely dense singularity, and then in a fraction of a second, it happened. The Big Bang. This wasn't an explosion in space, it was the explosion of space everywhere, all at once. In that first, blazing instant, the universe began to expand. It expanded faster than the speed of light. A process we call inflation. It went from the size of an atom to the size of a grapefruit in less than a trillionth of a second. This incredible expansion created space itself. It also created time, gravity, electromagnetism. The nuclear forces were born from this primordial chaos. The universe was a searing, chaotic soup of energy and exotic particles, a cosmic inferno where nothing familiar could yet exist. As the universe continued to expand, it also began to cool. Just as steam cools and condenses into water, the pure energy of the early universe began to condense into matter. For hundreds of thousands of years, the universe remained a thick, glowing fog. But as it continued its relentless expansion, it cooled down to a critical temperature about the same as the surface of a cool star. This cooling allowed for a monumental event. The free-roaming protons and electrons finally had slowed down enough to connect. They paired up, drawn together by the electromagnetic force to form the very first stable atoms. These were the simplest atoms of all, hydrogen-helium. The universe had just performed its first act of chemistry on a cosmic scale, creating the raw material for everything that would come later. The formation of these first atoms changed everything. Suddenly, the pesky electrons were bound up inside atoms no longer free to block the path of light. The universe became transparent. The light that had been trapped inside the cosmic fog was now free to travel unimpeded through space. This event, which we call recombination, released a flash of light that filled the entire cosmos. That ancient light is still traveling through the universe today. We can detect it with our telescopes. We call it the cosmic microwave background radiation. It is the oldest light in the universe, an echo of its birth, a baby picture of the cosmos when it was just 380,000 years old. With the universe now transparent, another force could begin its slow, patient work: gravity. The universe was not perfectly uniform. There were tiny, almost imperceptible variations in the density of the newly formed gas. Some regions had just a little more matter than others. Over millions of years, gravity began to pull on these denser regions. It was a gentle but persistent tug, drawing more and more hydrogen, helium gas into vast, sprawling clouds. These clouds were the seeds of all future structures in the cosmos. The Dark Ages were coming to an end as the stage was being set for the first stars to ignite and banish the darkness. After about 200 million years of darkness, something spectacular happened. The hydrogen atoms were squeezed together so tightly that they fused, releasing a tremendous burst of energy and light. The first stars were born. These were not like our sun. They were monsters hundreds of times more massive. They burned through their fuel in just a few million years and died in cataclysmic supernova explosions. But in their short, violent lives, they did something incredible. They forged heavier elements inside their fiery cores: carbon, oxygen, iron, and scattered them across the cosmos when they died. These first stars began to cluster, forming the first small infant galaxies. These early galaxies were small and misshapen compared to the grand spirals we see today. Over billions of years, these smaller galaxies were drawn together by gravity. They collided and merged in a cosmic dance of creation and destruction. Each merger created a larger, more massive galaxy. Our Milky Way is the product of countless such mergers over cosmic history. This is the grand architecture of the cosmos, sculpted by gravity over 13.8 billion years. For billions of years, the universe was busy building galaxies and enriching space with heavy elements. Then, about 9 billion years after the Big Bang, in a quiet spiral arm of the Milky Way, a new chapter began. A vast, cold cloud of interstellar gas and dust, the remains of countless generations of long-dead stars, started to collapse under its own gravity. Maybe the shockwave from a nearby supernova gave it the push it needed. As this nebula began to shrink, it started to spin faster and faster, flattening into a rotating disk. This spinning disk of stardust was the birthplace of our solar system. At the center of this spinning disk, matter became more and more concentrated. The pressure and temperature skyrocketed. A protostar began to form, gathering material from the surrounding disk. Finally, about 4.6 billion years ago, the temperature and pressure in its core became so extreme that nuclear fusion ignited. Hydrogen atoms began to fuse into helium, releasing an immense amount of energy. A star was born, our sun. Its birth sent a powerful stellar wind rushing out through the disk, clearing away much of the remaining gas and dust and illuminating the young solar system for the first time. Further out in the spinning disk, things were not hot enough to form a star. Here, tiny grains of dust, tiny grains of ice began to stick together. It started small. Dust bunnies grew into pebbles, pebbles into rocks, rocks into boulders. This process, called accretion, continued for millions of years. These larger bodies, called planetesimals, collided and merged, their gravity pulling in more and more material. In the hotter inner part of the disk, rocky planets formed: Mercury, Venus, Earth, Mars. In the colder outer regions, the gas giants formed: Jupiter, Saturn, and further out still, the ice giants formed: Uranus, Neptune. The solar system was a messy, chaotic place in its youth, but its basic structure was now in place: a star surrounded by a family of planets. Among the new worlds orbiting the young sun, one was special: the third planet from the star, our Earth. In its infancy, Earth was a hellish place. It was a molten ball of rock, constantly bombarded by asteroids and comets left over from the formation of the solar system. Its surface was a glowing ocean of lava, but even in this chaos, the planet was beginning to organize itself. Heavier elements like iron, nickel sank toward the center, forming a dense metallic core. Lighter materials, the silicate rocks, floated to the top, eventually cooling to form the planet's first crust. A truly cataclysmic event shaped Earth's future. Early in its history, a Mars-sized planet Theia smashed into the young Earth. The collision was unimaginably violent. It vaporized Theia and a large part of Earth's crust, sending a massive cloud of molten rock and debris into orbit. Over time, gravity pulled this debris together, forming a smaller sphere that began to circle our planet. This was the birth of our moon. This giant impact had a profound effect. It tilted Earth on its axis, giving us our seasons, and the moon's gravity would stabilize Earth's wobble, creating a more stable climate for eons to come. As the heavy bombardment of asteroids and comets slowed, Earth began to cool. As the planet cooled further, an atmosphere began to form. Volcanoes spewed gases from the planet's interior: water vapor, carbon dioxide, nitrogen. And as the planet cooled even more, the water vapor in the atmosphere began to condense. It began to rain. It rained for millions of years, a global deluge that filled the low-lying basins and created the first oceans. In the warm, chemical-rich waters of the early Earth, something miraculous happened. We still don't know exactly how, but about 3.8 billion years ago, non-living chemicals organized themselves into the first living cells, perhaps near deep-sea hydrothermal vents, or in shallow, sunlit pools. However it started, this was the spark. Life had begun. For the next 2 billion years, life remained simple. It consisted entirely of single-celled organisms: bacteria, archaea. They were tiny, but resilient. They filled the oceans and began to fundamentally change the planet. One group, cyanobacteria, developed a revolutionary trick. They harnessed sunlight to make their own food: photosynthesis. Photosynthesis released a waste product: oxygen. For over 1 billion years, these microbes pumped oxygen into oceans and air. At first, oxygen was toxic to most life. It caused a mass extinction, but it also created opportunity. Life began to adapt. Organisms evolved to tolerate and use oxygen to power metabolism. The Great Oxidation Event transformed our atmosphere and paved the way for complex life. Around 600 million years ago came the Cambrian explosion. Life rapidly diversified into complex multicellular animals. The oceans teemed with strange creatures. Trilobites scuttled on the seafloor. Anomalocaris hunted for prey. The blueprint for modern animal body plans emerged. Life had moved into the fast lane. Over the next few 100 million years, life conquered the land. This led to the rise of dinosaurs. For 150 million years they ruled the planet. 66 million years ago the age of dinosaurs ended in fire and fury. An asteroid 6 miles wide slammed into the Earth near what is now Mexico's Yucatan Peninsula. The impact unleashed the energy of billions of atomic bombs, triggering global earthquakes, tsunamis, a fiery rain of debris. A vast cloud of dust and soot blocked out the sun for years, causing a global winter that wiped out the dinosaurs and 75% of all species on Earth. It was a terrible extinction, but for one small group of survivors, it was an opportunity. The age of reptiles was over. The age of mammals had begun. In the post-dinosaur world, our distant ancestors, small shrew-like mammals that had lived in the shadows, began to thrive. They diversified, filling the ecological niches left vacant by the dinosaurs. Some grew large, some returned to the seas. One group took to the trees. These were the primates. Living in the trees favored grasping hands, forward-facing eyes for depth perception, larger, more complex brains to navigate a three-dimensional world. Over millions of years, one branch of this primate family tree evolved in the grasslands of Africa. They began to walk upright on two legs, freeing their hands to carry food and make tools. This was a pivotal moment in our history. Walking upright allowed these early hominins to see over the tall grass and travel long distances more efficiently. Their hands, now free, began to fashion stone tools to butcher animals and process food. This access to more protein and calories helped fuel the growth of an even larger, more energy-hungry brain. Then, about 300,000 years ago, we arrived. Homo sapiens. We were not the strongest or fastest animals, but we had a secret weapon: our minds. We, the children of the stars, had started to understand the universe. Here we are, at the very end of our journey, which is really just the beginning of our awareness. We stand on a small planet, orbiting an average star, in a suburb of one galaxy among hundreds of billions. It has taken the universe 13.8 billion years to produce us. We are the legacy of stardust, the beneficiaries of cosmic collisions, the survivors of planetary cataclysms. Our minds, the most complex structures we know of in the universe, are capable of understanding the very laws that brought us into being. This is a profound and humbling realization. The universe is not just out there, it is also in us. We are a way for the cosmos to know itself. Our quest for knowledge has only just begun. Every time we build a new telescope, we see farther into space and deeper into time. We have discovered planets orbiting other stars. We know that the ingredients for life are common throughout the galaxy. Are we alone? Is there other life out there, perhaps even other intelligent life asking these same questions? We don't know the answer yet, but for the first time in the history of our planet, a species has the ability to find out. We are sending probes to other worlds in our solar system and listening for signals from distant stars. The search is on. The universe still holds deep mysteries. We've learned that the stars and galaxies we can see make up only 5% of the cosmos. The other 95% is made of dark matter and dark energy. Unraveling these mysteries is the great challenge for the next generation of scientists. The cosmos awaits. Let's keep exploring. Let's keep looking up. The next great discovery could be just around the corner waiting to be found.